So probability is a measure of the likelihood of an event. How likely will something take place? What is the chance of snow tonight? I don't know. The weatherman probably does. What's the chance that you go home today after class? You know that. I don't decide. So many things have chances associated with that. But before we start with probability, we want to start with some definitions which may be useful before I define probability. Let's start with an experiment. An experiment is anything that has an outcome. Anything that has an outcome. Like taking your pen and trying to write on the paper. The outcome is it must write. If it doesn't write, you look around and ask for a friend for another paper, another pen, whatever it is. Because whatever you do, you expect an outcome. When you take the orange train from downtown, from Forest Hill, from Oak Grove, wherever it is, you expect them to drop you at Bunker Hill. That is the outcome. If they don't drop you here, you'll be mad. And probably you tell them that you have a class, they are delaying you, your professor wouldn't wait for you, and he's mean and all those things. Everything you do has an outcome. When you take a coin and you toss it, like the beginning of some of these games, it's heads and tail. It has an outcome. That is life. We experiment. You come to school, you expect to get a certificate so that life will be better beyond that. Are we going to get a certificate? We don't know. But there are so many outcomes that are out there. Some of you will transfer to a 4-year university. You put in a lot of applications to maybe 5, 6, 7 of them. You expect something out of that. Some will write you and say, we are sorry we cannot admit you, but we wish you the best in your future endeavors. And I'm like, shut up. If you're not picking me, I'm not interested in that. My future lied in your school and you know. All right. Or they'll say, congratulations, welcome to our school. It's an outcome. When you are hungry and thirsty, you can take food or you probably drink water. Sometimes when you drink the water, it doesn't even quench your thirst. That is an outcome. So you ask for more. That's the way it is. So life is full of experiment. You experiment so many things. Now, if you are able to put together all the possible outcomes of an experiment, it is called sample space. So sample space is a collection of all the possible outcome of an experiment. Number one, for example, if we have a couple that wants to give birth, they have two outcomes. You give birth to a boy or to a girl. So we put the pieces together. If you say that the possibilities are boy and girl, this is the sample space. You put it together. That's what we mean. You collect all of them and put them together. That is your sample space. If I toss a die, what you call dice, this is the plural. And that is a singular, a die. So that you just say, oh, okay, it's die. Whichever way, die, dice. Once you roll a die, it has 6 faces, right? You expect to get 1 or 2 or 3 or 4 or 5 or 6. These are some of the games at the casino. But then if I'm able to put 1, 2, 3, 4, 5, 6 together, I will call this a sample space. So a sample space is a collection of all the possible outcome of an experiment. So if I toss a coin, what is the sample space? It's heads or tails. These are all the possibilities. Make sense? Great. That's that. If you take a subset of the sample, we call it an event. So event is part of the sample space. And this, I believe, is in line with population and sample. Remember we started with population, that big set? We can't handle that, so we decided to take part of it, and we call it sample. It's the same idea here. We have a big set which is called sample space. Fortunately, this is manageable, so we can list all the members of this experiment. But then out of that set, if we pick something out, we call it an event. So for example, out of this set, we can choose to select all the even numbers, which is 2, 4, and 6. This is an event. Why? Because it is a subset of the sample space. Another person can choose to select all the odd numbers. That is another event. Or probably you want to pick a number that is more than 5. You pick a number that is more than 5, that is going to be 6. That is also an event. So far, so good? So we have an experiment. At the end of the experiment, you expect to have outcomes. And when you are able to think about all the possible outcomes and put them together, we call it a sample space. Now, within the sample space, if you decide to just select some of them, call it an event. And from there, we can define probability. So we haven't even defined probability yet. You know the the cards, right? Playing cards. The deck of cards. How many of you haven't seen or haven't used the deck of cards before? Have not. Haven't. Have not. Okay, excellent. So we've all seen it before. So the sample space of a deck of cards is 52. We have 52 cards in there. We have the red and the blacks, 26 red, 26 black. And then we have 3 different suits. Each suit had about 13 ranks. You need to know that. We'll be talking about that pretty soon. Maybe not today, but it will come up. All right. Great. So with this in mind, why don't we define probability? Probability of an event, meaning you can only find the probability of an event, not the sample space. So we say that the probability of an event is equal to the number of elements in that event. I think it's already here. Number of elements in an event divided by the total number of elements in the sample space. Come again. It's a fraction. So it's the number of elements in the event. You count how many. Remember like n? Aha. You count how many you have in the smaller set and divide by the number of elements you have in the big set. Let me give you a quick example. Let's assume you have about 25 students here. We have even more. So S, the sample space, will be equal to 25 students. And I look through male. We have about 6 male here. So we can find the probability of male because male is an event of that. It's a subset of this. So the probability of male in this class as we go through this lecture is 6 over 25. That's all we're saying. And I think we can revisit the example of the die, that the possible outcomes are 1 through 6. And so if I think of an event of even numbers, that would be 2, 4, and 6. And so if we are asked to find the probability of this event full of even numbers, you will count the number of elements in the event, which is 3, divided by the 6. That's the probability. That means that if you are asked to find a probability and you do not know the sample space, you are screwed. Because without a sample space, you can never find a probability. And without a sample space, you can't even find a subset. And so we're going to play around with a lot of experiment today. And I'm going to do a lot of them for you, and then I'll give you the chance to also think about some of them so that with time you'll be more comfortable finding the outcomes or the possible outcomes of different experiments. Is that okay? So now that we understand what probability is, let's talk about some statistical notation. How do we know we have a probability? I think when you see this, you know that is a mean, right? X bar. When you see that, we know this is the population standard deviation. Last week we talked about R, correlation. So how do we know we have a probability? I'm going to give you some notations. Awesome. And I think it's already here, right? No, it's not. Now, suppose that A is an event. Then the probability of A is denoted by P parenthesis A. It's a big P with a parenthesis. So when I see this, this represents probability of A. So what is this? Probability of B. Yes. What is that? Probability of M. This is not P times M. Unlike 097 where we were multiplying the variables. This is a symbol. So this time you are not thinking of the parenthesis as multiplication. It's part of the notation. So far so good? So now that we know the notation and how probability looks like, let's talk about some properties or some rules governing probability. Anytime you compute a probability, your answer must be between 0 and 1. That's the first rule here. Probability is always between 0 and 1. Oh, I think, yeah, okay, see in words. How nice. Between 0 and 1. So your probability can never be more than 1. So if I give you a test and for some reason your probability is say 50, like, yeah, I got a big probability, you know you're wrong. It can never be that. It's always a fraction, a bigger number in the denominator. Probability can never be negative. It's always between 0 and 1. So make sure that as you go through the computation, you will also be checking some of these rules. Make sure that you are staying within the boundaries. So far, so good? And the last one is the probability of the sample space is equal to 1. That's a general statement. And that's the probability for the sample space.
Always 1?
Yeah, the probability of the sample space is always 1. That is when you are so certain. The probability of being so certain of something is 1, like 100%. Come again? Where?
I mean, no, it's
T in what?
yeah, test statistic T. It's on the homework.
That's oh, we've discussed that. You came in late. Great. Now let's look at some examples. So if you haven't actually understood everything we've said this afternoon, this is the opportunity to have a better understanding. Because this is kind of practical now. It's not about is P of A, is between that. Now we want to just do great stuff. So, starting with the first example. A die is rolled once. In fact, this is supposed to be a fair die. Yeah. Make it a fair die. Because none of the dice you see in the casino is fair. But the point is, you can't prove it. They are all loaded. That's how they win all the time. Yeah, they are loaded. No. What it means is some of the die is biased towards lower numbers. Others is biased towards higher numbers. So if you happen to have one of them which is loaded towards or biased towards the higher numbers, anytime you toss it, you can get 4, 5, and 6. You never get 1, 2, 3. You will never know. They are smart.
So it's weighted. Yeah,
it's weighted, it's loaded. So when we talk about die, we are talking to the fair, we're talking about the fair die. The ones you have at homes. The one you see around, not the one in the casinos.
They provide you the ones?
Come again?
They provide you the ones that are...
Yeah, and they have their own die.
If they provide, how do you mean they provide?
Like
You're saying this, that they have faulty dice.
No, we
Are you
don't.
saying that people bring in faulty dice to win, or are you saying that...
Oh, no. They have it.
Oh.
They have it. If you want to play the game, you bet. Okay, I want 3 and 4. Look, they'll throw it. the big, whatever they call it. Those dice are weighted. Don't mind them.
Casino is fixed.
You're going to record it.
No, I'm just saying, that's what it's saying. The dice in the casinos are fixed. They're not fair dice.
No, it's not fair. That's it. That's what we're trying to say. And if you see a coin over there, the coin they toss for gambling and the rest, don't go near. They are smart. Very, very smart. Great. So we're talking about a fair die, where 1, 2, 3, 4, 5, 6, each of this side has equal chance of showing up. Good. If that is the case, what is the probability? What is the sample space?
1, 2, 3, 4, 5.
So we already have it on board, but I'm pretending we haven't even seen it. 1, 2, 3, 4, 5, 6. That answers the first question, right? Now let's go to the second part. What is the probability of obtaining an even number?
3.
Ah, thank you. So it started 3. And I was about to say, no, it cannot be 3. And she said out of 6. And then it completes that. And why do you say 3? Because there are 3 even numbers in here. Therefore, the probability is 3 over 6. Great. Can we go to the second one? Then the next one, the third part. What is the probability of obtaining an odd number? That's also 3 because we have 1, 2, 3 of them. So 3 out of 6.
So 3 is the event.
Yes. Yes. So odd is the event. What is the probability of obtaining a number greater than 4? It's 2 out of 6.
You never count the actual number they're asking you, right? It's just over.
Yeah, it says over that. But if it had been at least, we'll get there. Then we know you have to count the 4. What is the probability of obtaining a number less than 5? 4 out of 6. Any questions, any concerns? Everybody okay? Awesome. Now let's look at the second example. Yes. Mm-hmm.
Let's say if we get 3 out of 6 on the test, do we have to
Simplify. No, I don't care about that. This is not 093. So you can leave it as 3 over 6, 1 over 2.5, 50%. They are all the same. Example number 2. Now we're taking it to the next level. And I need you to think. A die, this time, is rolled twice, not once. Pay attention. And when you state that a die is rolled once, it's also the same as saying 2 fair dice rolled once. If you have 2 dice and you roll it once, it's the same as having 1 die and rolling it twice. It's a statistical statement, and it's true. Now, if we roll 2 fair dice once, how many outcomes are there? I hear 12, I hear 36. Which of them should I take?
36?
Why 36? Why not 12? Or why 12? Why not 36? It's a combination of the two. Now, in statistics, we have learned that when things become a little bit cumbersome, we use tables, like what we did in chapter 10 and chapter 3. So I'm going to use tables to explain these, and I believe you get to understand it. But before we draw the table, this is what we're saying. Remember, if you have 2 dice, let's say a red one and a blue one, it's possible to have 1 on the red and 1 on the blue. So that could be 1-1. It's possible to have 1 on the red and 2 on the blue, right? That could be 1-2. You can have 1-4. You can have 2-4. You can have 5-6. You can have 6-6, right? Yeah. So we try to list all the possible combinations. And sometimes it may be helpful to draw a table so that you can visualize everything. So this is what I'm going to do. Instead of trying to list these separately or individually, I will draw this simple table. We call this part roll. We're rolling the die. This is the first die. First die has 1, 2, 3, 4, 5, 6 on it. Second die has 1, 2, 3, 4, 5, 6 on it. Right? Die 1, die 2. It's going to be 36. So you're going to have 1, 1. You have 1, 2. 1, 3. It's possible to have 1 on the first and 2 on the second. 1, 4. 1, 5. 1, 6. Or you have 2, 1. 2, 2. 2, 3. 2, 4. 2, 5. And 2, 6. It's possible to have 3, 1. Now you notice that 3, 1 is not the same as 1, 3. Right? 3 on the first one, 1 on the first one. Excellent. 3, 2. 3, 3. 3, 4. 3, 5. 3, 6. 4, 1. 4, 2. 4, 3. 4, 4. 4, 5. 4, 6. 5, 1. 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So these are all the possible outcomes when a fair die is tossed twice or 2 fair dies are tossed once. Now, if 2 fair dies is giving us 36, how many outcomes will you have when you toss 3 fair dies? How do we know that? So over here, when we had 2 fair dice, this is what you did. You multiply 6 by 6, and you have 36. So if you have 3 of them, it will be 6 times 6 times 6.
260.
Somewhere there.
So it's always exponential?
Bomb. It's always the exponent. I wouldn't want to go for the exponential, but it looks like the exponential. Yeah. Can we list 216? Yes, we can. What are some of them? 1, 1, 1, because we have 3 of them. You can have 1, 1, 2. 1, 4, 4. You can have 3, 1, 2. 6, 5, 8. Oh, is that possible? Oh, okay. Why can't I have the 8? Because nothing like 8 on it. What about, okay, let's not go to 7. 6, 5, 0. I don't know. There's no 0, right? Awesome. So at least you know you can list them when I am not around. You can try all these things. Don't use a 0, don't use a 7, don't use 8, because on this die, it starts from 1 through 6. So you can list all of them if you so choose, and have about 216 of them. But we are not interested. We are only interested in this guy. That's why I took my time to talk about it. Meaning, it's possible to find its way on the 3rd test. See, we started setting the test already, yeah? Test number 3. This table, very, very relevant. And one thing about the probability test is all the questions on the probability test will come from your notebook. We will discuss all the questions in class. So if you don't have anything, then you know you have a big issue. But if you've been writing everything down, of course, make sure you understand it. Don't just copy. Now let's play with this table a little bit. Still on this table, I'm going to give you some questions on that. Now, do you know that the outcome on this particular table comes in pairs? Good. So if I use the word pair, I'm referring to a single outcome. So let's look at this. Suppose, this is a continuation of that question. An outcome is randomly selected what is the probability that the sum of the pair of an outcome is 1 or A exactly eight, B at most 8, C at least 8.
What's that last sentence? The pair of a what? Out is?
Oh, outcome. Thank you. So suppose you select any of these numbers at random or the pair. What is the probability that the sum of that outcome is exactly 8? What is the probability of that?
It's 8 cubed.
Let's try to understand the question first. What does it mean? What's the meaning of that?
How many of those add up to?
How many of those add up to
Exactly.
exactly 8? So how many of them over here exactly, it's exactly 8? No, you look through, I'm not answering that. You have to answer that. You see the numbers, right? It's right in front of you too. How many? Which of them? Is that all?
It's 5, actually.
Oh, I hear 5.
Oh yeah, 5 plus 3 and 3 plus 1.
It literally, it's a diagonal, like graph. Like,
Once you understand the question and what you've been asked to do, you will notice that we are talking about these guys. We want all the pairs. When you add, sum means add. 6 plus 2, 8. 5 plus 3, 8. This 8, 8, 8. How many of them do we have? So what is the probability of selecting an outcome? 5 out of. Excellent. So here is 5 out of 36.
oh, I get the at least. I see it now.
Now we go to, are we okay? Can I go to the second part? At most. Now, at most, I think it's on the next slide. Let's look at the definition first. Is it here? Yeah, there. Great. Check the next slide. You have the definition of at most and at least. At most means less than or equal to. Keep that in mind. Statisticians like putting that on exams. And then we have at least, greater than or equal to that number or more. And at most, that number or less.
So anything above that line would be at most.
Come again.
15 out of 36.
So if we say at most, say 8, what is the meaning of that? 8 or less. So plus that line. That line and up will be at least. And down will be at most. Don't allow these words to mess up your brain. Because the way sometimes we use the at least and the at most. So let's start with at most. So you said this is 8 and what? 8 and lower. So you go to the table, add all of them, and select the sum that is 8 or less. So it's going to be 26 out of 36. Confirmation? Yeah. How did they get that? Here. This is 8, 8, 8, 8, 8. Anything below that is less than the 8. So you count 1, 2, 3, da, 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 you get 26 of them. Can I continue? Awesome. So the answer to this is 26 out of that. How about at least? What's the meaning of at least? 8 and above. So anything that is equal to 8 or more. So we're looking at 8, 9, 10, 11, and the 12. And you said that is 15 over 36. Is that okay? So we are done with the die. Now let's go to coins. Because we play with the quarters and the dimes and the nickels and all the time. We see referees and umpires of a game using it almost all the time, trying to decide who kicked the ball first or who start the game first, whichever way it is. But I want to learn the probability associated with these two. So I'm going back to the previous slide. A fair coin is tossed once. If you have a coin and you toss it once, what are the possible outcomes? It's heads or tails. Somebody's already computing the probabilities for us, which is awesome. So over here, your chance of getting head is 1 out of 2, right? That's why we say 50%. You've been using it, but now you can do the computation. But we are not interested in tossing the coin once. That's nothing. We want to toss a coin twice. Or we want to have 2 coins and toss it once. And that's what we have here. A coin is tossed twice. Or 2 fair coins are tossed twice. When we finish with twice, we go to thrice. 3 times. But let's consider the twice. Having a coin tossed twice or having 2 coins. Fair coin is tossed twice. And we're saying that's the same as 2 fair coins tossed once. How many possibilities are there? How do you know it's 4? You have 2 outcomes on the first and 2 outcomes on the second. So 2 times 2, just like the 6 and the 6. Remember that? Yeah. Can we list them? Yes, we can list them, even without tables. So what are the possibilities? You can get heads and tails. You can get tails and tails. You can get heads and heads. And you can get tails and head. So you can list these without necessarily drawing a table. But since I started with a table, maybe I'd like to continue with the table. If you can list this is not relevant. It's not necessary. Don't waste time. So here we have 1 and 1. This for the first coin. Second coin, heads and tail. We are tossing. So H and H will go together. H and T. You can have T on the second, T on the first. So H on the heads on this, or this is the second and first, whichever. And then we have TT. So these are the possible outcomes. Is that okay? Let me give you some questions on these too. If an outcome is selected at random, what is the probability probability of obtaining A, exactly one head, B, at least one head, C, at most two tails. Two fair coins are tossed once. We have listed the possible outcomes, so we have our sample space. With our sample space, we can do anything. Come again.
I mean, exactly one head.
Yeah, it's exactly one head,
2/4.
and the next one will be at least one head, and the last one is at most two tails. So I hear 2/4. Any confirmation? She's saying 2/4. Is that right? 2/4. Why is it 2/4? So we're looking for exactly one head. So look at all the four. Which of them has exactly one head? This guy and that guy. So 2 out of 4. We have 4 of them. She's right. 2 out of 4. And you can simplify this if you want.
But if it's greater than or equal to, since it does have an H, why wouldn't it count?
Because that would give you
It will give you 2. We are looking for exactly 1. Now let's look at the second part. That is if you're okay with part A. At least one head. What is the meaning of that?
At least. More is fine, but you have to have one.
More is fine, but at least you need to have, we're using the at least again. We don't want to use at least again.
1/3.
3/4.
So let's define at least one first before you give me the answer.
Greater
Greater
than
than
or
or
equal to.
You are still using at least.
One head or more.
One head or more. That's the meaning of that. At least one means one head or more. So we're looking through. So we're looking at 1, 2, 3, up to wherever we can get to. So it's going to be 3/4. So one head, we have 1, 2, and more than that. That's what makes it 3/4. Any concerns? 3/4. Third one, at most 2 heads. What's the meaning of that? So,
2 or equal to.
come on.
2. Take T.
Wait, isn't that tails?
Did I say heads?
Yeah.
I take my heads back. Now I say tails.
Up to or including 2 T's, no more. So it's 3 out of 4, right? 2. I can't see.
Oh, I'm sorry.
1/4.
Less than 2 is okay, but no more than 2.
Yes. So,
So it's 2/4.
Less than or equal to.
If you have 1, that's
So,
fine, but no more than 2.
you're looking for
It is.
2 tails,
You're right, it's the tails, but you have less.
1 tail, no tail. At most, is that number down. So what would be the answer? To be 4 out of 4, which is 1.
So it includes the HH.
Yes, because it has 0 tails.
Oh, that is a trick question.
I know, it is. It is. So this is 4 out of 4, 1. So now that I have a feeling that you kind of have some sort of understanding, we would like to look at the 3 coins. We will list all the possibilities together, and then I may give you some questions to try. I'll give you time to practice that, because that example is an examinable question.
For example, you're gonna give us right now?
Yes. And it remind me to make chapter 4 homework available before we go. Otherwise, I haven't. I don't think I have it up there.
This is chapter 4 we're doing.
This is chapter 4. Come again. Did I? Yeah, no. You already have the PowerPoint. Do you have the ones I sent earlier on? Yeah, it's already in there. It was only chapter 10 which wasn't part of the PowerPoint. All right. So let's look at when a coin is tossed 3 times. A fair coin is tossed 3 times. How many elements are we expecting in the sample space?
What? 8.
Why 8?
It gets exponential.
What is the number of elements in the sample space?
6.
Why 6? Going to be 2 times 2 times 2, like we did with 6 times 6 times 6, and we had 216. So it's 2 times 2 times 2, because each coin has 2 outcomes. Suppose this is my coin, that's my coin, that is my coin, the head of one president, another president there. This has 2 chances, two possibilities. So you multiply them, you get 8. Like when we had the, that thing. Nice. Doesn't look nice. We have 3 of them, you multiply 6, 6, 6, right? So over here, how many outcomes should we expect?
8.
All right, so help me list the 8. Waiting. You can have tails, tails, tails. You can get, you see, they are coming up the simple ones. Heads, tail, tail. Tails, head, tail. Tails, head, head. Head, tails, head. 1, 2, 3, 4, 5, 6. 2 more. Heads, heads, tail. Tail, tail, heads. These are all the possible combinations. How did we know that? It's because we have 3 coins. So it's possible to have T, 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 H, 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 or you can have T here, and H there. We look at all the possible combinations. But pretty soon I'll show you how to list this without necessarily drawing a table. I've already given you the table. There is another way of doing that. We call it tree diagram. We're not there yet. So when we get there, I'll show you the tree diagram. You remember the factor tree? You might have done that in high school, not here. Factor tree. Oh, yes, you do. When you have, say, 12, and then you have branches to the factor tree. Remember that? Oh, no. Don't worry, you'll be fine. All right. So why don't you solve these based on this data? If an outcome is selected or randomly selected at random, with time you get to know that the probability statement is kind of one way. It's always selected randomly. At random, what is the probability of selecting A exactly 1 head, B exactly 2 tails, C at most 2 tails, and D. I mean, you can add more. You can add the at least later. I wanted to add at least, but I've changed my mind. At most, 3 tails. Or you can also add at least 2 tails and answer it. I'm going to give you some time. What is the answer to the first one?
7 over 8.
I think 3 out of 8 is,
A or B? O, B. Oh, okay. Because we have only 3 outcomes that has exactly 1 head. What are they? 1, 2, 3 of them. It has only 1 head. That's what we're looking for. B. Exactly 2 heads. What is that?
2 over
2?
Yeah, 2. No, exactly 2.
Yeah, exactly 2 tails.
3 over 8.
Oh, okay.
So in that one, the TTT is included in that, correct?
That's 3. We want exactly 2. How about at most 2?
7.
Hey, now you understand the system. Yeah, how nice. It's 7 because we counted H. That is 0 tails.
so wouldn't it be 8 out of 8?
Which at most,
No, D would be 8 out of 8.
this will be 8 out of 8. But this, we will not be using the TTT, the 3 heads, 3 tails.
I don't understand, at most 2 tails, why is it?
At most 2 tails means we're looking at 2 tails, 1 tail, no tail.
So it's 1.
Which one is 1?
Well, number 9 is 8 out of 8, right? 'Cause
Oh, it looks like a 9. D,
So D is gonna be
8 out of 8. I'll take that.
So could you say 1 or?
Yeah, same thing. Any concerns? So I believe now we have some idea about probability. And probability is not the same as odds. Remember odd? They are not the same. Let me try to explain. Odds do not take into consideration the sample space. So for example, if odd ratio, assuming we have about 7 students, 7 male in the classroom, male against 1, 2, 3, about 18 students, 18 female, right? If I want to find the odd ratio of male in this class, it will be 7 over 18. And the odd ratio for female will be 18 over the 7. That's how we calculate the odd ratio. But if it's probability, then we need to find the denominator, which is the samples with the bigger set, before we divide by that. That's what I'm saying, because most of you will hear odd ratio. What is the odds that this, and that? It's not the same as probability. They are different. Good. I think I have time. So let's talk about complement of an event. I've already explained the first 2, right? At least at most. Complement of an event. This is a mathematical complement, and I think the spelling is also different. Hey, you look good. That's a compliment. Whichever way it is. Come again? No, this one they don't look. Do you remember alpha from chapter 10? What was the definition?
Margin of error,
How did we define it?
Like a numerical value or?
If it's a numerical value, what does it mean? If it's a oh, we didn't say it was a margin of.
It's a variance.
No, it's like there's a possibility, like
Critical value?
no, it's not like the possibility that there is an error, but you don't know. If
No, wait. It's that
Can
there's a
continue what you said.
probability that what are we talking about this? Probability that your critical value is.
You kind of have the idea, but I'm looking for something else. So if we say probability of snowing today is 90%,
Majority of the data is.
what is the
you have nothing to
what is the alpha?
The chance that it won't.
It won't. 10%. What's the probability that you'll be in school tomorrow? Oh, it's about 95%. Meaning there is a 5% chance that you will not be in school. Yeah, that's what you meant. I knew that's what you wanted to say. That was the alpha in chapter 10, right? In chapter 4, it is called complement. So you notice it's the same thing which we are giving different names to. Like we took equation of a line from last semester's 097, and in this class we call it regression equation. Remember that? Y equals to mx plus. It's the same thing. That's mathematics. As you advance, it's the basic things. We revisit the basic, we give it a different name, and this time we make it more applicable to life. Like, oh, okay. So the complement of an event is the probability that it will not occur. So it's nothing new. We've already seen that in chapter 10. Complement has a notation. So when we say we have probability of A, the complement of A, the probability that A will not occur, A will not take place, will be denoted by A raised to the power C. Or you can call it A superscript C. Because raised to the power, I said that so that you can relate, but it's not raised to the power C anyway. We can also use this. A raised to the power S lined 1. It's a subscript, lined 1. Now this is called, or is pronounced A prime. Some authors also use the A with a bar on top. And the reason why I avoid the use of this in this class, I think it's pretty common in your textbook too, but don't confuse yourself with the mean. Remember, anything with a bar is a mean. This, if you see a P here, at least you know we're talking about the complement, not the mean. So if I write P of X bar, this is no probability of mean. It's the complement of X. Success this. So now we have the definition and then the notation. Let's talk about the mathematics. For example, if probability of A is 0.7, what is the probability of A prime?
What do you say that A prime was? No, 7 then.
negative 6. No, 0.7. Point,
Hold on.
It's 0.
It's whatever will make it 1.
Excellent. It's whatever. Come again?
How is it?
Because this is the same as 70%. And 30, 70 will give you 100. That's why this is 0.3.
So much easier.
Oh, wow. I'm happy to hear that. They both have to add up to 1 if it's decimal, but if it's percentage, they must add up to 100. But I hope you haven't forgotten that decimals, fractions, percentages are all the same. If you lose focus of that, it's going to affect you. What's the probability? If probability of D is 0.65, what is the probability of D complement? 0.35. Because this is 65, that is 35%. When you add the two, what do you get?
100.
Or 1. 100% or 1. Now she got it. Awesome. Great. Last example. Probability of F is 0.8. What would be the probability of F prime? 0. When you add the two, what do you get? 1. That's what you have here. That when you add the complement of probability to the probability itself, that must give you 1. So now you understand that statement based on these examples. I don't want to add more.